Hello physics students. Up until this point in this topic, we've been studying capacitors in a general sense. And we learned that a capacitor can be any two metals, like these pliers and this pulley. And I can charge, if I charge one of these up positive and the other one up the same amount of coulombs but negative, then these will attract, and I can exploit that attraction by connecting these two with a wire, and then the electrons traveling from the negative back to the positive will release energy through whatever they go through. So we have been studying capacitors just in general, and whenever we encounter a capacitor, we were just given the capacitance of the particular device. But now we're going to shift gears a little bit in this topic, and we're actually going to derive formulas for some regularly shaped capacitors. So there are three general shapes that we're going to study. The parallel plate capacitor today, which I've already mentioned, is just two sheets of metal that are parallel to each other, flat, not curved, a certain distance apart with a certain area to each sheet of metal. That's called a parallel plate capacitor. Then we're going to be studying, after that, spherical capacitors, a sphere within a sphere, so positive, negative maybe, and then cylindrical capacitors, two cylinders, one inside the other, charging up one positive, one negative. And what we're going to be doing over these next three videos is deriving the capacitance from the geometric shape and size of the particular capacitor. So today, like I said, parallel plate capacitor. So here's the topic for today, and we're going to be deriving this formula, which I just wrote down on the first day of capacitor. Well, we're going to actually derive this formula. A reminder here with a picture of what a parallel plate capacitor is: two sheets of metal, each of area A. So this area is not the area, if we have 1 meter squared here and another meter squared here, we don't plug in 2 here. It's the area of one of those sheets and then the distance apart and epsilon 0. And we charge these up. Now the first thing that we do is we follow a process, or what we do is we follow a process with 4 main steps to it for all the geometries. The first thing we do is we start with the definition of what capacitance is. It's how much charge you store for a given voltage. So for a given voltage, the more charge something stores, we say it has a higher capacitance or a higher capability of storing charge in it. So we start with this formula, but in order to move on, we've got to figure out what the voltage is in all 3 cases. So then the way we determine voltage is we first determine the electric field. We do that with Gauss's law. So we imagine here this little parallel plate capacitor. We draw a Gaussian surface, a little box, and when we look at the shape, we know that there's only going to be electric flux through this bottom surface because the electric field is 0 here, 0 here, and in between the plates, it goes from positive to negative. And so there's no flux through the sides, only through the bottom. Okay, so that's what the left side becomes E over times area of our Gaussian surface. Not the area of the whole plate, right? Only the area of our Gaussian surface. That's the flux coming out of our box. And then that's going to be equal to Q enclosed, sigma, which is the total charge over the total area of the plate, times the area of our Gaussian, inside our Gaussian surface. Sigma times area gives us the coulombs inside our Gaussian box over epsilon 0. So let me create a pause here in case you need an opportunity to catch up. Okay, so that's our derivation of electric field here. We cancel out the Gaussian surface and we're left with that formula. The next step, the third step in our derivations, is now that we have the electric field, we calculate the voltage so we can plug it in here and evaluate. Now normally voltage is the negative integral of electric field over a displacement. But in a parallel plate capacitor, since the electric field is constant, we could just say electric field times distance. Basically, we're going to take E out because it's constant and integrate dx, which just gives us the distance between the plates. So here is our voltage. When we plug in the electric field in here, it gives us that expression. Now, finally, we go back to this C equals Q over V, the definition, C equals Q over V, and we just take this, flip it over to bring it up to the numerator, and we get our formula. So let me create a pause in case you need a chance to catch up with that formula. Okay, so again, I want to emphasize you should be making these steps in your mind, the 4 major steps, because we're going to be doing them for all 3 geometries. Start with Q over V, then know that you've got to get rid of this V, so that means getting the electric field. Then from the electric field we can get the voltage, 3rd step, and then get the voltage out of there, plug it in, and what will happen is the charge always cancels because the capacitance only depends on the geometry of the object. So there it is. More area, more capacitance. The closer the plates are together, also the more capacitance. Okay, so that's one thing for today. The other thing we're going to do is do a couple derivations. One thing you're responsible for in the curriculum is deriving the energy in a capacitor. First day I wrote these formulas up on the board. The energy in a capacitor is 1/2 QV, 1/2 CV squared, 1/2 Q squared over C. So you have to be able to derive those. So that's the next step. Oops. Now, don't write this down, but normally the energy, if you have a voltage, it's Q delta V. But the problem with this is assuming all the charge goes through a voltage that's constant. But with a capacitor, as the charge is leaking off and we're depleting the energy out of it, the voltage is also going down. So in order to figure out the energy, we have to use this expression, but only for a small amount of charge over which the voltage is constant. And then we could say if we just let the charge drop a little bit in a capacitor, like maybe just let a couple electrons come off that capacitor, then this is the amount of energy. Again, energy is voltage times charge. As long as the charge is small, the voltage doesn't vary much, and that will be an accurate expression. But we don't want just the energy of a couple electrons. What we want is the energy of, as we're discharging from, or charging from 0 to Q. So what we're going to do is integrate this and get the total charge. But first what I'm going to do is eliminate voltage as Q over C. Oops, little q. Now where does that come from? Remember, C equals Q over V. So if you solve for V, it's Q over C, and that's what we use to get rid of the voltage here, okay? All right, now, like I said, we can figure out the total energy in the capacitor as we're charging or discharging it by adding up all these little bits of energy. Let's say we're charging it from charge 0 to some final capital Q. I'm going to separate this out. And we're integrating Q dQ, which just integrates to Q squared over 2. And now I can plug in my limits, and I'll combine the 1 over c and the 1 over 2 as 1 over 2c, and I get my final expression for the energy to charge this capacitor is 1/2, or actually, yeah, I'll do just q squared over 2c. But there are two other forms. For example, from this formula, if you want to get rid of the charge Q, then what you have is CV equals Q. So if I put that here, I got C squared V squared on the top over 2C, which gives us, if you simplify, 1/2 CV squared. Or if I wanted to get rid of the voltage here, the capacitance, C equals Q over V, then if I put Q over V here in for C, then what I'm left with is 1/2 QV. So these are some other forms also, just by taking this derivation and then using this formula to get rid of either of these variables. Okay? So energy in a capacitor. All right, let me pause to give you a chance to jot that down. Okay, let's move on. Another thing that you have to derive is the energy density in a capacitor. So the energy density, we use the the symbol lowercase u instead of capital U. And what we mean by density, remember the first density you probably learned about was mass density. Grams per volume, right? Mass per volume. So that now we're going to calculate energy per volume inside the parallel plate. So we begin first by saying that the energy density will be the total energy in the capacitor over the volume. And I'll write out volume because if I just put V, it'll look like voltage, okay, which it's not. It's energy per volume. So what we have already determined is that this is the energy. So I'll put that on the top, Q squared over 2C. And then on the bottom, the volume of a parallel plate capacitor will just be the area times how far apart the two plates are. Because basically, parallel plate capacitor makes like a box. If you take the surface area here and multiply by the height, that gives you the volume between the two plates. Okay? So continuing on, what I'm going to do now is get rid of some, or simplify this a little bit. And then what I'm going to want to do is get rid of the C and get rid of the Q to get an expression that only depends on electric field. Okay, that's our aim here. So the first thing is the C I can get rid of using this, epsilon 0 A over D. Okay? And then the charge we can get rid of from, in terms of electric field. Remember that the electric field in a parallel plate capacitor is sigma over epsilon 0. And the sigma is the total charge over the total area. So we derived this earlier in our notes today. And so the charge is equal to the electric field. If I move this to the other side over here, area epsilon 0. Okay? So, as I said, I'm going to take this expression, put it here, and then this expression will go in the top here. And I'm going to simplify, and then I'll have an expression for the energy density just in terms of the electric field and constants, as we'll see. So on the top, we've got this squared, the Q squared, giving us E squared and on the bottom, I've got 2 times this, the C, oops, and then that's C right here, and then I also have AD. So well, if you look carefully, you'll be able to see that this A squared is canceled by this A and this A in the denominator. So all A drops out of the formula. One of the epsilon zeros here cancels one of the epsilon zeros here. This D cancels all the D's. So all the A's, all the D's drop out. What's left over is the 1/2. The electric field squared and the epsilon 0. And there is the electric field, the energy density inside a parallel plate capacitor. And it's an interesting result because it shows that setting up an electric field has energy. There's energy in an electric field, okay? This much energy density. Everywhere there's an electric field, there's a little bit of energy density in that region. So kind of fascinating idea that the electric field itself is energy, okay? But again, this is part of the curriculum. You have to be able to derive this total energy over total volume, and then you use the expression we got over here, and then get rid of the C and the Q with electric field and capacitance, and it'll simplify to that, okay? So basically, again, if that comes up, that's what you have to be able to do. Couple more things for today. What I want to also show you is what happens to the various things in a capacitor if I start separating the plates, okay, or bringing them closer together. And there's 2 different scenarios we're going to look at and investigate. What happens if I just charge these 2 plates up, one positive, one negative, and then I don't take any of that charge off? The way we would say that is that the plates then remain electrically isolated. No charge can escape. And then I separate these further out. And then we're going to think about what's going to change in terms of charge, electric field, voltage, energy, when that happens. And then we're going to look at how all those various things change or don't change if instead of the plates being isolated, they're connected to a battery, and then I separate them. So that's the final thing for today. Okay, so So here is my before. What I have is a capacitor like this, plus Q minus Q. And what I'm going to do is put 0 here, because that may change. Because what I'm going to do is I am going to change the system. Oops, not before, after. This plate is here, and then what I'm going to do is spread this out to double the distance of separation. So right like this. Maybe if this is D0, this is now 2D0. What happens, for example, to the charge? It turns out that if the capacitor is electrically electrically isolated, the charge cannot change. So the new charge is equal to the old charge. We could go ahead and put that in on the diagram here if we want. But the charge doesn't change. Now, if the charge doesn't change, the electric field also does not change. How do I know that? Well, remember, we had this expression where the electric field inside a parallel plate capacitor is the charge density on the plates over epsilon 0. We derived this using Gauss's law even earlier today. And so, if that's true, and the charge doesn't change, the charge density doesn't change, and that means the electric field doesn't change. What about the voltage? The new voltage, it turns out, is twice the old voltage. How do I know that? Well, I know that the voltage is electric field times distance inside. It's really the electric field integrated, but when the electric field is constant in a parallel plate capacitor, we could just say ED. Now, if the electric field's the same as before, but the distance over which it applies is now twice as great, the voltage will be twice as great because that larger distance. And then last thing, the energy. What is the energy, the new energy in the capacitor? It turns out it's twice the old energy. The capacitor would gain energy if I spread it out. And how do we reason that out? Well, remember, electrical energy of a capacitor is 1/2 QV. There's one equation for the electric field in a capacitor. So if I have the same charge as before, but twice the voltage, I'm going to have twice the energy. And the interesting question is, where did that energy come from? Energy cannot be created or destroyed, right? So if suddenly our capacitor gained energy, it came from me, right? If I want to spread this, these are attracted. If I let them go, they're going to snap together like two magnets. So in order for me to spread them, I've got to pull them apart, right? I've got to put a force times the distance on that top plate. And so I'm doing work, right? I put work in, I'm putting energy in. So that's where the energy comes from, me, when I spread this apart, okay? So this comes from work. To spread it apart. All right. If you need a moment to catch up, then I'm going to add a pause to allow you to catch up. Okay. Last thing, case 2. We're going to increase D for a capacitor that remains connected to a battery this time, not isolated. So this is the before picture. We've got our capacitor like this, plus Q, and then minus Q. Let's do zeros on those. A certain distance D apart. Maybe I'll put the D over here because what I want to do is hook up a battery like this. Voltage 0. Okay. After, what I have are the same plates, so they're like this far apart. Oops, kind of crooked, but they're further apart, so like so, right? So further apart. It's crooked, but that's all right. Now, what is this new charge? Is it the same as before if we are remaining connected to the battery? Well, the first thing that's obvious is the voltage can't change because the battery's maintaining that with the chemical reactions. So it's not the charge that remains constant this time, it's the voltage. The new voltage is equal to the old voltage. The next thing we could reason out, 2D over here, is that the electric field must decrease. Okay, E new is 1/2 the E old. How do I know that? Well, remember, voltage is electric field times distance. If this is staying constant because of the battery, then if this increases, that has to decrease by the same proportion. Doubled, half the electric field. And that means that the new charge has to also decrease. So why does it have to decrease? Well, remember, electric field is sigma over epsilon 0. And if the electric field's getting smaller, so does the charge density, so does the charge. Okay, so less charge now. Where did that charge go? It can't just disappear. Charge is also conserved just like energy. Had to go back into the battery. Okay, so by doing that, I'm forcing charge into the battery. And then the electrical energy. Now, well, it's going to be 1/2 of the original electrical energy. How can I reason that out? Well, again, electrical energy in a capacitor is 1/2 QV. So if I have the same voltage as before, because the battery remains connected, keeping it constant, but the charge went to 1/2 what it was before, I'm going to have 1/2 the energy that I had before. And then the question is, where did that energy go? It disappeared out of the capacitor, but energy cannot be created or destroyed. Had to go somewhere. It went back into the battery. By forcing charge backwards into the battery, I'm also forcing energy. I'm recharging the battery in a sense. So this went into battery. Okay, that's where the energy went. All right, let me create a little pause in case you need an opportunity to catch up. Okay, so that's it for today. A lot of little things, probably made a kind of a long video, but the key thing that you want to focus on that's most likely to come up on the AP is deriving the capacitance expression C equals epsilon 0 A over D. And remember, there are 4 steps to that. There's going to be 4 steps to the other 2 derivations we're going to do. The same 4 steps with the details different. So you better remember those. Okay, the first step, do you remember? Start with C equals Q over V. Okay, so we start there. And then what we want to do is get rid of this. So that means the second step is you find the electric field, knowing that you're going to have to find the voltage. So you derive E using Gauss's law. Then you derive voltage using integration, or in this case, just E times D, integrating the electric field. And then finally, you substitute that voltage expression right here and simplify the formula, and you'll have the formula for the capacitance of that particular geometry. That's the thing you want to focus on when you're studying these notes. All right, so I hope you enjoyed. I'll see you in the next physics video.